So, parameterization, what is it all about? Parameterization can seem complex for someone using it or hearing about it for the first time. It was a difficult topic to understand, but it's important as it's used in multiple topics this year and next. We aim to deliver a relatively straightforward and practical explanation of what it is, and then go through some step-by-step examples of how it can be used. Parameterization is used to rewrite variables such as x and y in terms of a common parameter t. We can say that a parameter is some kind of variable that drives the x and y coordinates in the two-dimensional coordinate system, so it describes their movement along the xy plane.
Let's look at a basic example. Yx equals x plus 4 squared. We can define our parameter t to be whatever we want to be. In this case, for sake of simplicity, let us define t equals x plus 4. If we substitute t into the expression for y, we got that yt equals t squared, and we got that xt equals t minus 4. With this, we have just changed the dependence of both variables x and y. We made them both dependent on t. Another common example of parameterization is xt equals cos t and yt equals sin t. This is also called a parameterization, or a system of parametric equations. Since we have defined two variables x and y in terms of parameter t, which can also have the form of phi or theta. Let's now talk about the true and more complex applications for parameterization in mathematics. Let's draw into parameterization in line integrals.
Line integrals are defined as a scalar product between f and dr, where f describes a given vector field. Line integrals are to be solved in one dimension, the same number of dimensions that a thin line has. The operation is fairly straightforward, and if you know how the scalar product works, then you should obtain an expression like this. In both definite and indefinite line integrals, it's important to maintain the one-dimensionality for every component. So we would require that fx would depend solely on variable x, and the same for the fy and fz components. Take that our fx, fy, and fz components do not only depend on variables x, y, and z respectively. In this example, we're given a function f, where they ask to determine the line integral over the segment that goes from the origin to the point 1, 0. We can see that our fx now depends on y and our fy depends on x. If you solve this without parameterization, you get an expression like this, which you can't solve because y becomes a constant in the fx component, and after integration, it does not have values corresponding to it, causing the line integral to not have a singular solution. So we know that the function must undergo parameterization, and the way we parameterize it is the following. So in short words, because you're dealing with a line integral, which is one-dimensional, all components must be one-dimensional as well. So it becomes easier to just rewrite all components in terms of a single parameter, when the function becomes more complex.
The same happens when you increase the dimensions in which you're integrating over. Surface integrals integrate over 2 dimensions, and therefore all components should have a maximum of 2 dimensions as well. Take this example. Evaluate the area of surface z equals x squared plus y squared, that is inside cylinder x squared plus y squared equals 9. The question already tells you how to parameterize. Here x and y become parameters. The fx component is one-dimensional, so is fy. Fz is two-dimensional because fx and fy both depend on the chosen parameters. They do not need to be rewritten. Z is not a parameter and must therefore be parameterized. In this example, you are required to use cylindrical coordinates, so you must change coordinate system. The change is straightforward, so just pause the video if you would like to attempt it yourself. Parameterization also works in upper dimensions. The logic follows as we have studied it. If you're dealing with volume integrals, then each component must have a maximum of 3 dimensions. So if they are dependent on 4 variables, you must choose 3 parameters, which can be 3 of the already existent variables, and rewrite the 4th dimension in terms of chosen parameters.